Hi. Okay, so today we're gonna go have a brief go over for complex numbers. It has been my experience that some of the things here folks have seen in high school, much of the things here folks have seen in high school or in calculus class, but that some of the things will be new. So just again, trying to give folks a chance to everybody's on the same footing. Okay, so we want to start by describing what the complex numbers are about and how they work. So one of the problems that a person runs across when you try to teach the complex numbers is that a lot of times people think they don't make any sense. So want to emphasize that they do make sense. That in fact you're driven to them. So consider a physics problem. We're told the position and the velocity of the cannonball. So you have a cannonball, it's like a snapshot in space, and you're told the position and velocity, and you're asked what time will it hit the ground. So when you apply Newton's laws, and you do all the acceleration due to gravity kind of stuff, and then you get a quadratic equation, and you go to solve the quadratic equation, and there's two solutions because it's a quadratic equation, so it's got two roots. And one of the solutions is the answer that you want, and the other one, you notice, has an answer of negative time. So you might reject that as not physical. It doesn't make sense to have negative time. But in fact, that's not really right. In fact, the negative time turns out to be, when you think about it, how long ago the cannonball was shot from the cannon. So that is to say, it has something to tell you. There's something there it's trying to let you in on, and you're just not listening. Okay. So historically, when you look back through the history of intellectual life, when you look back through the history of science, history of mathematics, in say the 1400s, when people solved equations that got answers that we would today write as the square root of -5, they threw them out as unreal or imaginary. Over time, though, people started to notice that these numbers seemed to work sensibly. In particular, when you go to solve cubic equations, fourth power equations, etc., the if you just handle the algebra like regular algebra, it all works. Okay, so let's take an example of what I mean. So consider x squared minus 9 equals 0. It's a perfectly good equation, kind of thing you see in high school or in calculus class or whatever all the time. So you write x squared minus 9 is the difference of two squares, x minus 3 times x plus 3. So you get the two solutions, x equals 3 and x equals minus 3. So pretty boring. So now x squared minus 8. Okay, the only twist there is that 8's not a perfect square, so you have to work with the square root of 8. But it's all the same. X is positive square root, x is minus square root. So it's all very boring. And in general, x squared minus a decomposes into x minus the square root of a and x plus the square root of a. And you follow the regular rules of high school algebra, x minus the square root of a, x plus the square root of a. You distribute here the x and the minus square root of a. So x and the minus square root of a. And when you multiply it all together, it comes out to be x squared minus a, irrespective of whether a is plus or minus, positive or negative. If, for example, a is minus 9, then the square root of a is imaginary, but that doesn't seem to be any breakdown. Nothing happens to the universe, the clocks don't stop or kind of stuff. The algebra all works. So in the 1500s, when people finally started solving cubic equations, they found that they were often working with expressions that look like this. I have the cube root of 2 plus the square root of, and then it happens to have a minus 11. If they followed the usual rules of algebra, they would, when they multiplied all that stuff together, just like as we did here, if they followed the usual rules of algebra, they found that they got the right answer. So people became more and more comfortable treating these as numbers, as perfectly legitimate expressions that you manipulate according to the regular rules. And in fact, by the time we get to the middle 1800s, the sort of 1840s, 1850s, 1860s, people who are working in physics, engineering, chemistry, this kind of stuff, are increasingly coming up with systems where these kinds of numbers form a part of the physical universe. So by the time Maxwell comes up with his equations in the late 1860s, and they depend fundamentally on these imaginary numbers, it's clear that in fact the universe is built with these kind of numbers. So in fact, when a person says, I have had folks say to me in a classroom or friends of mine or whatever, these numbers don't make any sense. In fact, it's the opposite. In fact, the universe seems to be built that way. Okay, so time for a definition. So we write I, of course, for the number with the property that I squared is minus 1. I'll just remark that electrical engineers, some other engineers write J for that number because they're determined to be obstinate. They write I for current. Anyway, so you can see J. For example, the Python language likes to start with J. So by definition, I is the square root of minus 1. Now, since this is a number, we can multiply it by other numbers. If you have, for example, 5 times I or 12 times I or minus 3 times I, then that's called an imaginary number because of the history that I just went over. So numbers like the square root of minus 2 are imaginary because you take square root of minus 2, you're under the radical, you write 2 times minus 1, you break out the square root of 2, and you're looking at square root of 2 times I, so that's a pure imaginary number. Now, if you don't just multiply these by by reals, if instead you add them to reals, why then you're looking at something like a plus bi, where a and b are real. So examples, these are called complex numbers. Examples are 5 plus 4i, or 2 minus I, or minus 1/9 plus 0i. So really, a real number is a special kind of complex number, particular case of a complex number. The set of complex numbers is denoted with this C. That's called blackboard bold, so it has an extra line in the C, so that people used to write it on a blackboard that way. When we had blackboards with that way, just as we often use X or Y for real numbers, you often use Z for complex numbers. So you might write Z equals A plus BI. It's just a convention, but if you don't know the conventions, then you're in a little bit of quandary. So if you have a complex number, a plus bi, z equals a plus bi, then the real part, re of z, is a, and the imaginary part, im of z, is b. So the operators just pull out the a and the b. And of course, two complex numbers are equal if they have the same real part and also the same imaginary part. Okay, so this is a simple definition that just starts with adding I to the real numbers, and then you use all the regular high school algebra operations, and you end up with things that look like a plus bi. All right, so time to talk about those elementary operations. So I want to be able to add, subtract, multiply, and divide these numbers. So the complex numbers use the same high school algebra rules that you're used to. Addition and subtraction, very straightforward. If you want to add two complex numbers, you add the real parts and you add the complex parts. Real parts and you add the imaginary parts. Forgive me, I misspoke. If you want to subtract two complex numbers, you subtract the real parts and you subtract the imaginary parts. Okay, so that's the simplest thing that could possibly happen. In fact, that's what happens. Multiplication. So when you do multiplication, you do what you think you do. For example, here I have a0 plus b0i multiplied by a1 plus b1i. So I distributed the a0 and the b0i. All right, so here we go. I get a0 a1, a0 b1i. b0i times a1, b0i times b1i. And I'm just doing like high school algebra. So this is what people did in the 1500s. They just said, okay, so we're going to chug along and see what happens. Okay, A0, A1, there we go. A0, B1I is, I have A0, B1, and I brought it out an I. There's a B0, A1I. There it is, B0, A1I. I don't know, I wrote them in alphabetical order. So I brought out the I from these two middle terms. And then finally, with the last term, there's an I and an I, so that's I squared. And there's a B0 and a B1, so I separated those out. When I take the I squared, that's minus 1. So I have minus 1 times B0, B1, and there it is. Can you see it? It moved over to there. And here is the A0, B1, A1, B0 times I moved that over to here. So I end up with something of the form A plus BI. I end up with something that has a real part and a pure imaginary part. Okay, so multiplication works the way it works in high school. The formula is a little bit, might take you a few minutes to memorize it, but it's just straightforward high school stuff, that's all. So some, oops, hit the wrong button. So some quick examples here. 3 minus 2i times 4 plus 0.5i. So you can have non-integers, you can have negative numbers there. And of course, the 3 and the 4 adds to 7. The minus 2i and the positive 1/2i adds to minus 1 1/2i. And the other examples are no more complicated. 3 halves plus 8i minus 2 plus I. So 3 halves minus 2 makes minus 1 half. 8i minus 2i makes 6i. And then here's the multiplication. And again, the multiplication is simply high school rules. It results in a somewhat more complicated formula than the sort of grade school multiplication formula, but not all that much more complicated. 1 plus 2i, 3 plus 4i. So I'm following the rules here. I get 1 times 3 minus 2 times 4. And remember where the minus sign comes from. It's because of I squared. Anyway, 1 times 3 minus 2 times 4 turns out that adds to minus 5. And then I have 1 times 4 plus 2 times 3. Turns out that adds to 10. Okay, so this is the regular high school multiplication. Multiplying them isn't totally straightforward, but it is a plug and chug type of operation. Now I haven't done division yet. You'll see it at the bottom of this slide. So it takes just a bit more work to do division. Division is always harder than multiplication. That's kind of a steady theme throughout mathematics. That division is typically trickier than multiplication. Okay, so just some definitions before I get to division. So where z is a plus bi, then the conjugate is a minus bi. So you change the sign, the sign, of the pure imaginary. If b was positive 7, now you've written in a minus 7. If b was negative 7, now you've written in a plus. So you change the sign of the pure imaginary part. All right, and then by direct computation, it's clear that if you give me z equals a plus bi, I could compute the real part by taking z plus the conjugate over 2. See, the conjugate is denoted with a bar over the z. And the imaginary part is z minus the conjugate over 2. That's where you just go through them, and that's the way it works. And then each one of these rules is just as straightforward. If you take the conjugate of the sum of 2, it's the same as the conjugate of the first plus the conjugate of the second. And I'm not going to do all these rules, but just as an example here. So the conjugate of a plus bi is a minus bi. The conjugate of c plus di is c minus di. And so all you see is that the pluses change to minuses on the one side of the equation to the other. That's all. Likewise, conjugation is preserved by multiplication. Induction, from the prior formula, induction gives you this, that the nth power of the conjugate is the conjugate of the nth power. This one down here is especially easy. If you have a plus bi and you conjugate twice, you change the sign and you change it back, you end up back to the original number. And then the last one here. If you take a number and you multiply it by its conjugate, you get a squared plus b squared, and that's an especially important one, and it's also a familiar one. So a plus bi times a minus bi, and you recognize that as the difference of two squares. So you're going to get a squared, and then you're going to get b squared. A squared, and you're going to get b squared. So if this said x minus y and this said x plus y, excuse me, I have that backwards. If this said x plus y and this said x minus y, when I multiply them together, the familiar difference of two squares formula from calculus is that you get x squared minus y squared. But when you take minus bi squared, the I squared gives you another minus, and so when all the smoke clears, you end up with a plus. So a complex number times its conjugate is the squares of the two of the real and the imaginary coefficients. In particular, complex number times its conjugate is greater than or equal to 0, and the only time it's equal to 0 is when the number itself is 0. So it's natural to define that the length of z is, we use absolute value bars, of course, is the square root of a squared plus b squared. So in other words, it's a square root of the number times its conjugate. So if you said to yourself, well, I could define all kinds of crazy operations, why are we defining this particular crazy operation? For example, why don't you change the sign of a? The answer is because of length. That's why. Conjugate is convenient because of length. So that's exactly what conjugate is about as far as we're concerned. Okay, direct calculation also gives that if you take the length of z0 times z1, so you multiply z0 times z1 and then take the length, you'll get the same as if you take the length of z0 and then multiply by the length of z1. So direct calculation meaning just simply calculate it. using the multiplication forms from the prior slide. And so we get the formula for division. If you want to take the inverse of a number, then you want to take the number over its length squared. That is to say, if you want that z0 times z1 makes 1 plus 0I. If you want that z0 times z1 makes 1, then you're looking at this. What do you have to multiply by? Well, you have to make sure that it comes out to have length 1. Except, of course, in the special case that z is 0. The inverse of the 0, of the complex number 0 plus 0I is undefined. Okay, so we got the division, but it was just a little bit of a detour. We had to talk about length first. Okay, so time for pictures. So it's very common to plot complex numbers in a picture. You have one axis for the, if you're looking at a plus bi, you have one axis for the a part and one axis for the b part. And just as an example, 2 plus 3i, I went over 2 and up 3. For minus 3 minus I went back 3 and down 1. So that's no more complicated than that. It's called the Argonne plane after the man who invented it, Parisian bookseller. Anyway, after the man who invented it sort of popularized it. It's very convenient to be able to see pictures, of course. A person knows from calculus it's very convenient to be able to see pictures, and this is how you can see pictures. In particular, I just want to talk about conjugate and length and the pictures, what the picture says for those. So let's talk about conjugate first. Here's a plus bi, here's a minus bi. So you change the sign, the SIGN, of the second component, what we would call the y component in high school. So a plus bi changes to a minus bi. And here, of course, if you start out with a negative b, so this is something like, this is minus 1 plus minus 2i, and then when you change the sign of the minus 2, you're looking at minus 1 plus 2i. So basically, the conjugate reflects across the x-axis. Okay? Of course, conjugate is related to length. Anyway, I wanted to draw a picture that showed length. So if you give me a complex number here, to find the length, you just simply take the line and connect the complex number to the origin, and that's the length formula gives you what you think it should give you, the square root of a squared plus b squared. It's no more complicated than that. Just do that. Okay. So far it's been very straightforward, and in fact a person could say, you know, why don't we just say these are like vectors? So fair enough, but we're getting to something that is that's genuinely different. In order to get to the thing that's genuinely different, I need to consider polar form. So if z is a plus bi, then we have, you know, from the formulas in calculus class, that a is r times cosine theta and b is r times sine theta, where r is the length of z. That's called the modulus. And theta is the arc cosine of b over a. It's called the argument. So the angle that it makes with the x-axis taken counterclockwise, with a counterclockwise sense. So it's exactly what a person is used to in calculus. Okay, so in that case, then you can factor out the r's between the r cosine theta and the r sine theta. You can factor out the r's, and you're looking at z is r times cosine theta plus I sine theta. Z is r times cosine theta plus I sine theta. Okay, and that, just like a plus bi is a familiar form, this will also be a familiar form when you work with complex numbers. One advantage of this form is that it plays nice with multiplication. When I introduced multiplication and I just chugged along with the high school rules, you know, it was a little ugly. Not awfully ugly, but a little ugly. And so here, polar form works a lot better. Let's take two complex numbers and multiply them together. So I have r naught cosine theta naught plus I sine theta naught, r1 cosine theta 1 plus I sine theta 1. And you just multiply. So this is four things multiplied together, the r naught, the r1, the theta naught stuff, and the theta 1 stuff. So here's the r naught times the r1, and here's what happened when I multiplied the theta naught stuff times the theta 1 stuff. Well, we've done this just a minute ago, so the theta naught stuff is a cosine times cosine, and there's going to be sine times sine, but the i's are attached, so I have an I sine and an I sine, and we know what happens when you multiply two i's, you get a minus. Okay, all right, and then what else do you get? Well, you get cosine times I sine, and you also get I sine times cosine. So I factored out the I, and there's the cosine sine and the cosine sine, and I think I did. I could have lost a subscript somewhere, but basic algebra gives you what you got here. I think pretty sure, pretty sure. Now I don't know that a person would recognize this, but you've seen this formula before. This is the formula for the cosine of theta naught plus theta 1. You saw it a long time ago in high school, and you probably forgot it. We use it once or twice in calculus, but anyway, probably forgot it. Fair enough, but I need it now, so there it is. And this is the formula for the sine of theta naught plus theta 1, the sine of theta naught plus theta 1. So there it is. So I quoted those formulas. They might be out of the dim, dark past, but nonetheless, they're perfectly legitimate trigonometry formulas, so it's legitimate to quote them. So what I'm looking at here is that the product of two complex numbers, when you write them in polar form, is actually reasonable. You multiply the r's. Oh, it says r naught, r2. I'm sorry, that's a typo. It's supposed to be r naught, r1. Apologize. So you multiply the r's and you add the angles. The modulus of the product, the modulus of the product, the r's, the modulus of the product, except that I made a typo. The modulus of the product is the product of the moduluses. It's actually moduli, but I hate that crap. Anyway, the product of the modulus of the product is the product of the moduluses, and the argument of the product is the sum of the arguments. What's the angle? It's theta naught plus theta 1. Theta naught plus theta 1, that's the angle. What's the modulus? It's r naught times r1. Okay. If you apply a complex number to itself, that is, you square the complex number, why, you get that you take the square of the r's and the n times the angle. So this is called de Moivre's theorem, that the power of a complex number is you take the power of the modulus and the product, the n times the angle. And in particular, it has the special case that z to the minus 1 gives you r to the minus 1 cosine of minus theta and sine of minus theta. So in the case of an inverse of the reciprocal, you're looking at the inverse of the modulus and the negative of the angle. So just as an example, I'm going to find the two square roots of I. So I is a perfectly good complex number. It actually happens to be pure imaginary. I'm going to find the square root of I. I itself is the square root of minus 1, but now I'm going to find the square roots of I. Okay, so let's have a whack. So we're looking here at z squared. I'm taking n to be 2. So z squared is r squared cosine 2 theta I sine 2 theta. So I'm taking n to be 2, and I just simply wrote down what it is, equals I. Okay. So we know that the modulus of the product is the product of the moduluses, and the argument of the product is the sum of the arguments. So I have to worry about what's the modulus. Of course, I squared is minus 1, so I need to have an r of 1. Think about the complex plane. I is up there at what in high school you would have called y equals 1. So the length of I is 1. So we've got to take r to be 1 in order to have the formula work out. Right? In order to have the formula work out, we're looking for z squared equals I. I has a modulus of 1, so we need r to the 2 equals 1. There we go. Okay, so what about the angle? I need that twice the angle gives, well, what's the angle for I? The angle for I, the angle for I is 90 degrees. It's pi over 2. There we go, pi over 2. The angle for I is pi over 2. Okay, so I need twice theta is pi over 2. Well, obviously pi over 4 occurs right away to a person, but also 5 pi over 4 after a moment's reflection occurs to a person. 5 pi over 4 doubled is 10 pi over 4. Take away the 2 pi, that's 8 pi over 4. 10 pi over 4, take away the 2 pi is 2 pi over 4. And that's pi over 2. So we're looking at the two roots. Are 1 times cosine pi over 4 plus I sine pi over 4, and 1 times cosine 5 pi over 4 plus I sine pi over 4. 5 pi over 4. Okay, so we found the square root of I using de Moivre's theorem. Like I can't. So the fundamental thing about the complex numbers, the most single important fact about the complex numbers is this. We're not going to talk about it anymore, but I can't resist quoting it because it's key. So a degree n polynomial, a regular high school degree n polynomial, powers of x, that has coefficients that are complex. They can be real numbers, that's fine, but they can also be things like 2 plus 3i. A polynomial that has coefficients that are complex has n many roots in the complex numbers. A person remembers that if you stick to the real numbers, then you have things like x squared plus 1 equals 0 that don't have any roots. So the complex numbers are great because if you have a polynomial of degree 7, it will have 7 roots. Some of them could be repeated. You could have same root twice. That's fine. But if you have a polynomial of degree 104, it will have 104 roots. So it all makes perfectly good sense. It's not less than 104 roots. It's exactly 104. Anyway, well, we're not going to do anything more with that, so I'm going to pass by. But I couldn't do the complex numbers and not mention the fundamental theorem. Okay, last thing to talk about here. It's the tricky part. It's the part that, I don't know if that is tricky, but it's the part that, in my experience, folks have not seen before. If you haven't seen anything, then this is the thing you haven't seen. Okay, so you remember, well, first I want to observe about the powers of I. That if you write I to the 0 equals 1, because anything to 0 equals 1, I to the 1, of course, equals I squared is minus 1, of course, that's the definition of I cubed is I squared times I, so we get minus 1 times I to the 4th is I squared times I squared. So that's minus 1 times minus 1. So you're back to 1 again, back to 1 again. So the powers of I make this kind of circle. Dun, 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 4 points on a circle. Okay, anyway, and then the second thing on this that I need for this slide is that I want to recall the power series expansion of e to the x from calculus 2. So e to the x, you remember, or you take the rising powers of x, and on the bottom of the fraction goes the rising factorials. 0 factorial, 1 factorial, 2 factorial, etc. Okay, so Euler plugged in I times t. So you plug in I times t, and off you go. You're looking at what is e to the I times t, and off you go. All right, okay. So I times t to the 0, I times t to the 1, I times t to the 2, I times t to the 3, I times t to the 4, etc. The bottoms of the fractions are the factorials. Now, I went up as high as 4 because it's going to be the highest relevant power of I. But anyway, so off you go. Okay, so what happens when you take I to the 0? Why, anything 0 is 1. I didn't bother to write it. What happens when you take I? There it is, it's I. What happens when you take I squared? You get minus 1. What happens when you take I cubed? You get minus I. And then what happens when you take I to the 4th? You're back to 1 times. So what you see in here in this expression is you still have the rising powers of t, but they do different things. The odd powers of t, here, odd powers of t, the t to the 1, t to the 3, they have an I in them. The even powers of t, do not have I's in them. Okay? There is sometimes negatives and sometimes not negatives. But the key thing here is that the even powers of t do not have an I. The odd powers of t do. So I'll break it into a with I and without I case. Here's the with I case, see the I there? And here's the without I case, see the no I. There are some minus 1s, and you have to worry about what numbers are on the bottom of the fractions. If you're looking at the evens, you have the evens on the bottom of the fraction, so the even number is factorial, and t to the even number. If you're looking at the odds, the 1 and the 3, if you're looking at the odds, then you have the odd number in the power and the odd number on the bottom of the fraction in factorial. Okay, so I broke this e to the it into 2 expressions. One involves the even ends, and one involves the odd ends. And now's when you return to calculus 2 and you say to yourself, I know that. I know that power series expansion. I recognize that from calculus 2. That's the power series expansion of cosine t. And I know that power series expansion. I recognize that power series expansion from calculus 2. That's the power series expansion of sine t. So this, which looks like a terrible disaster, simplifies to cosine of t plus I sine of t. E to the it is equal to cosine of t plus I sine of t. So when we're writing r times cosine t plus I sine of t, we can instead write it as r e to the it. Isn't that nice? Isn't that just beautiful? And an even more beautiful thing happens when you plug in t equals pi. When you plug in t equals pi, you recognize that the sine of pi is 0, and the cosine of pi is the x component is -1. So e to the I pi equals -1. Isn't that an awfully nice formula? It involves there all those familiar numbers from calculus. Just beautiful formula. Euler's relation. Just beautiful. Just magnificent. Okay, so the regular power series expansion from calculus 2, with a little bit of plugging and chugging and being careful about subscripts, gives cosine t plus I sine of t, the polar form. And so we're able to write complex numbers as involving the e to the it. Okay, that's it. That's it for complex numbers. I'm going to ask you, of course, to do a little practice, but not all that much practice, just a couple of problems to check that you're able to work through the parts. You'll remember, right, that if, for example, you take e to the 1 plus minus pi I, that you can break that into e to the 1 times e to the minus pi I. But other than that kind of stuff, this is all very routine. Okay, very good, very good.